All right, for part 2 of Lewis structures, we get a set of molecules that will not obey the octet rule very well. And since they're going to be mixed in with the others, you need to know how to identify them. If we look at IF2, we're going to go through the same process we did before. Count all the electrons and see how many bonds this molecule has. Each of the halogens has 7, so that gives me 21. And there's an extra negative charge there, so it gives me 22 electrons. All right. There are 3 atoms times 8 gives me 24 electrons to fill the octet, and we called that the happiness, which means there are 2 electrons missing to make them all fill the octets, and they share those in bonds, which means this only has 1 bond. And that should leave us with a little bit of confusion, because there are 3 atoms. I cannot bond one bond with 3 atoms. So you will come across some of this math where they have extra electrons in them and the sharing doesn't work out. If I have more bonds, that's fine, because we can get multiple double and triple bonds and resonance, but we're going to cross all this out. We don't want any of this. This 24 is not going to matter anymore. The only thing that we want is this 22 electrons right here. So we're going to go back to our IF2. We know iodine's in the middle, and we're going to put the fluorines on it. All right, we'll spread those guys out. And let's just take an inventory of these fluorines first. The outsides are always going to have their octets full like normal. The inside atom, the central atom, will have extras, or let's just see what happens here. Each one of these fluorines has 8. So 8, 16. I need 6 more to get to 22. That 22 is of the utmost importance. If I had a traditional dot structure like that, that only gives me 20. So I actually don't want that dot structure. I'm going to have 3 lone pairs on this, and I'm going to spread them out like a triangle, kind of like we did before, like that. So there, this iodine atom is breaking the octet rule. It has 2, 4, 6, 8, 10 electrons on it. How is that possible? Well, iodine is a very large atom with a -1 charge, so we put that in brackets like we always do. And its extra electrons can actually be stored in the unoccupied d orbitals, because it has open d orbitals in its valence shell. So we are allowed to break the octet rule. Carbon dioxide. Let's go back to the second one here. Carbon dioxide, we say, this is a simple one, but let's just go through the math anyway. For CO2, carbon has 4 valence electrons, each oxygen has 6, so 6, 12, and 16 electrons. 3 times 8 gives me 24 to fill the octets. Octets make them happy. That means they are missing 8, and they are going to share those in 4 bonds. So we evenly distribute those double bonded oxygens. This is just a good structure to memorize. But we can do this with simple octet rules, or Lewis structures as well, because each carbon needs 4 bonds, each oxygen needs 2, so they split them up, and we get a structure like that. Okay, next one is XeF4. We count all the valence electrons there. Each fluorine has 7, so 28. And another 8 for the xenon gives me 36. Now you're saying, wait a minute, noble gases don't bond. Well, sometimes some of the bigger ones do. Things get more complicated as the atoms get bigger. And then there are 5 atoms times 8 gives me 40 electrons in order to fill all the octets and make them happy, which leaves me deficient 2, or 4, which gives me 2 bonds. And that's where we say 2 bonds, that doesn't work, because there are 4 atoms. So I don't need that. Those 4 bonds are not accurate. This does not take care of everything, but I do need to mind these 36 electrons. So xenon, central atom. Fluorines on the outside. 1, 2, 3, 4. Let's fill all the fluorine octets. and count all those up. Let's see what's left. Got 8, 16, 24, 32. I need 4 more to get to 36. Those are going to be in sets of 2. They go on the central atom. Extra electrons just go in the middle. So that xenon now has 6 sets around it. It has 4 bonds and 2 lone pairs. It's got 6 sets of electrons. And it's big enough that they're stored in d orbitals. Draw a Lewis structure for CO3. So here's another resonance structure. Let's calculate those electrons here. We've got 6 for each oxygen, so 6, 12, 18, 22 with the 4 for the carbons, and 2 more, which gives me 24 electrons. There are 4 things times 8 gives me 32 to fill the octets and be happy, which is a difference of 8 over 2 shared in bonds. We get 4 bonds. So 4 bonds with 3 atoms around the carbon means we have extra and we get resonance. So we get double bonds here. So the carbon's going to go in the middle, oxygen's on all the outsides, and I have a 4th bond. So where does it go? Well, it can go there, or there, or there. And if you were paying attention on the last one, we say it actually goes to all 3. And we draw arrows in between them. We're going to put the -2 charges everywhere. And we need to fill in the dot structures. The double bonded one will have them in a triangular shape. And the other ones get 3 sets. And ran out a little bit of room here. Okay, so what does that even mean? It's not that that bond is moving, like we said before. It's that what really happens is that double bond, it's actually bonded everywhere. It is almost like there is all 3 of them connected with a single bond. So it's not a single bond or a double bond. That extra 1 bond is shared between 3 spots. So it's actually like these are all 1.3 bonds, 1 1/3 bonds. This kind of tells us it's actually an average of all of them. When we draw all 3 structures with all possible resonance, that the real molecule is an average of all 3 of them. And that average is what we call bond order. If it was a single bond, it would be a bond of 1, bond order of 1. If it was a double, it would be 2, triple would be 3. But this can actually have a third of a bond because that resonance structure distributes it in 3 spots. We get a bond order of 1.33. So here's what's the bond order of nitrogen in the NO3? Well, this looks identical to the carbonate. The charge is a little different. Structure's not exactly the same, but the resonance is the same. It's the triple bond with those 3 oxygens. We have another 1.33. For F2, there's a single bond between those fluorines. We call that a bond order of 1. Oxygen, diatomic, has 2 bonds. We call that a bond order of 2. And nitrogen, 2 nitrogens will make the triple bond. That has a bond order of 3. And then if we're really, paying attention, we want to put those lone pairs on as well. Fluorine gets them on all 4 sides. Oxygen's going to make a triangle out of them because there's 3 regions with that double bond. And then the nitrogens, notice we put them on the outside, so it's 180 degrees away from the bond because there's only 2 regions. We call the single or the double and the triple bonds, we kind of count them in 1 region of space. Here we can see with the bond orders that the actual bond length gets smaller. So single bonds, double bonds, and triple bonds, my bonds get closer, the atoms get closer and closer together. They also store more and more energy. So we do still talk about the potential energy in those bonds and how close that attraction is. If they have more than one bond, it just makes sense. There's more energy in those and they can get closer together. So how would you rank bond length and strength for these single bonds? So all of the carbons are the same. We want to put them in order of smallest to largest. So our chlorine is going to be able to get the closest to that carbon, and then the bromine is going to be in the middle, and then the biggest one is going to be the iodine. So the chlorine CCl bond is going to be the smallest or the shortest, and it'll have the most energy as well, because those atoms are closer together, and Coulomb's law tells us that when they get closer together, there's a stronger attraction. And here's the data for that. So we can see that the Cl is the smallest, bromine, and then iodine, and we can measure the energy in those bonds as well to verify. Now, formal charge is when the octet rule is not strictly followed with the Lewis structures that we would expect. I shouldn't say the octet rule, just the Lewis structures. We get a structure like this for NH4+, and this doesn't match what we'd expect for the Lewis structure for nitrogen. Hydrogens are doing what they're supposed to, but if we just looked at the nitrogen, we would expect it to do this, to have 3 bonds, but it has 4. It still fits the octet rule, everything's still good, but when it doesn't fit its normal Lewis structure, it's because it has a formal charge. And it's kind of a way to map out in the structure. We've got this positive charge here. Where are the electrons distributed in the structure itself? If we look at that nitrogen in the structure, how many electrons is it responsible for? Now I'm only going to count, let me use a different color here. I'm only going to count the electrons on the nitrogen. So if I'm sharing those bonds with the hydrogens, the hydrogen has one, the nitrogen has one. That's kind of how we're looking at this. And if we look at this, we say, okay, the nitrogen only has 4 electrons, but typically it has 5. That means it lost one, and it has a formal charge of +1. To write that, we just put a positive charge by the nitrogen, and we circle it to show that that positive charge, that formal charge, is on the nitrogen. If we do the same thing for the nitrate structure, we can just pick one of those. Remember from previously that it looked like this. And we'll get those at the triangle. Okay. So it's going to help us. We need to compare to the nitrogen and to oxygen by themselves. Oh, sorry, that's a -1 ion. But when we compare to the nitrogen, like before, has that dot structure. Oxygen has that. So we expect nitrogen to have 3 bonds. We expect oxygen to have 2. That's not always the case. So they have a formal charge in the meantime. Let's look at the nitrogen again, and we see that it has 1, 2, 3, 4 electrons around it. Let's get those a little bit more clear. So that means that nitrogen has a positive formal charge. This oxygen up here has 1, 2, 3, 4, 5, 6 on it. We count those single from the bonds. That's what it's supposed to have. It's supposed to have 6 electrons. They don't have to be in the same order, but they've got 6, and it normally over here has 6. So 6 and 6 is good. These other oxygens, however, they have 1 extra over here from this bond. They each have 7. So 6 of their own, and then this extra 1 here for 7. Normally oxygen has 6 electrons. These have 7, the way that we're defining it. That means each one of those oxygens has an extra electron. So each one of those has a formal charge of -1. And we circle it like that. And you will also notice that those 2 formal charges of -1 each and that positive charge, they reduce down to the charge of the molecule, which is -1. If we did carbon monoxide, which looks like that, and we compared to its normal dot structure. Now this is a neutral molecule. That doesn't mean it doesn't have formal charges, it just means that they're balanced. For the carbon, carbon has 2 of its own electrons and then 1, 2, 3 in the bonds, so carbon has 5. Typically carbon only has 4. So carbon has an extra electron. This is a minus formal charge on the carbon. Oxygen has 2 of its own and then 3, 4, 5. So oxygen has 5 as well around it. Typically it has 6. Oh, make that an oxygen. So it's missing one. It has a positive formal charge, and you see those cancel each out. So the molecule is neutral, but each one does have a formal charge. If we looked at CO2, technically here both of these are valid structures. If we zoom in here, and we use formal charges to distinguish between them. So we'll put these at those triangle markers, this one over here. They all have the same number of electrons. They all have 4 bonds to share to fill all their octets. But this one on the bottom is actually a valid Lewis structure by the rules that we have. But formal charges don't work. If we looked at carbon and oxygen, we know their dot diagrams. Carbon should have 4 electrons around it. Oxygen comes in with 6. So let's see how that matches up. At the top, this oxygen has 2, 4, 5, 6, and the one on the right has 6 as well. So those look good. The carbons have 4 bonds around them, so we count each one of those electrons once. Carbon has 4. Those match. There are no formal charges on the top structure. On the bottom, however, my carbon is still good. It has 4 bonds, so each one of those electrons counts once. One of those electrons are on the carbon. So carbon does not have a formal charge, but the oxygens, this one on the left with those 3 bonds, that means oxygen has 5 electrons. Typically it has 6. So it's missing one. This has a positive formal charge there. And the oxygen on the other side has 6 of its own and an extra one there, so it has 7. That actually has a negative formal charge. So that oxygen is negative. Those formal charges aren't balanced. They're on different sides of the molecule, and they can balance out, so it kind of just goes into that structure over there. So this one is not the stable version of CO2. Even though it looks like everything could work, formal charges is kind of the last check to see does it work or not. So draw all the possible structures and select the most stable for SCN. And when they write it like this, they mean the C is in the middle for SCN. So let's calculate this one. SCN minus, sulfur has 6 electrons, carbon has 4, that gives me 10, nitrogen's 5, 15, and an extra one. We have 16 electrons here. There are 3 atoms times 8, 24 to be full of the octets, which gives me, this is going to give me 4 bonds. Okay, so we've got 3 different options here. I've got 3 things: carbon, nitrogen, and sulfur. And if I get 4 bonds between those things, I can have a triple bond on one side or the other, or double bonds on one side or the other. And we'll fill in all of their octets. And then we see formal charges. Can we eliminate anything here? For the carbons, each one of those carbons is going to be okay. Carbon needs 4 electrons, and in the middle here this has 4, this has 4, this has 4. So all the carbons are okay. What we really need to worry about is the nitrogen, which should have 5, and the sulfur, which should have 6 electrons. So we just let's start comparing those. Sulfur, let's look at all those. The top structure, sulfur has 4 of its own, and then 5, 6. That one's good. This sulfur has 2 of its own, 3, 4, 5. That's going to give me a formal charge on the sulfur of +1. And the sulfur on the bottom has 6 of its own and an extra 1. So it has 7. Typically it has 6. So this is a minus sulfur charge. Nitrogens, let's go through those. Nitrogen has 4 of its own on the top, and then 5, 6. Typically it has 5, so now I have an extra electron on the nitrogen, so we'll give that the minus over there. This nitrogen over here has 6 of its own and a 7th. Well, nitrogen only has 5, so this one's really different. This has a formal charge of -2. And I'm actually going to put that with 2 minus signs like that. So we'll separate them. It's just kind of a thing for formal charges. And then don't forget we have all of these guys in brackets anyway because they're ions. We say -1. I should have written that with the Lewis structures. If we look at the nitrogen on the bottom, that one's okay. It has 3 of its own, or 2 of its own, and then 1, 2, 3 from the triple bond. So that has 5. So that one's stable. So we want the least amount of formal charges possible. What that's going to do is eliminate this middle one. Those charges are not evenly distributed. Got the nitrogen with -2 and the sulfur is deficient. Those electrons will not stay that way. But the other two look like they could be correct, and they might even be in resonance with one another. Our last consideration is electronegativities. What's more stable? Is that electron on the sulfur more stable, or this electron on the nitrogen more stable? And we know nitrogen's more electronegative, so when we do formal charges, we're going to say this is the most probable structure for the SCN with that double bond. Although electron could go to the other side, sulfur is pretty electronegative as well. Those could be in resonance, but if you had to pick one, we'd definitely go with the top one. The least formal charges on the most electronegative atoms.